Hopefully you guys hear me. Do you guys hear me? Yes, no, maybe so.
Yes.
Yes, thank you. Great. Sorry. I now hear you. Okay. First thing I want to talk about today, other than apologizing for my lateness, just customary, is the date of the final exam. The college has a very weird, I mean, to me, it's a weird way of designating the timing of final exams. And so we meet on Monday at 2 and on Wednesday at 1. And so if you look at, it's ambiguous as to which, there's one final exam date assignment that applies to if you meet Monday at 2, and there's another final exam assignment if you meet Wednesday at 1. And so I went with the later date. But I am concerned, and I just posted it to Blackboard. The date is Wednesday, sorry, not Wednesday. It's Monday, I want to say May 24th. Just double check that at 10:30, which is a weird time to have an exam when your class meets at 2. But that is one of the recommendations. Monday, May 24, 10:30 till 12:45. So the first thing I want to ask is, and you can just indicate on the chat if you have a conflict with that date. Okay. So if you do have a conflict with that date, get in touch with me. Like, if it's normal that at least 1 or 2 people write the exam at a different day and time. But if like half of you have a conflict with that date, then we'll reschedule. But my assumption is that you guys prefer to have more time to prepare for the final than less. And that's why I went with May 24th instead of the May 19th. The other option was May 19th, which is like 2 weeks from today. And, we haven't even covered the last 2 lectures. So I didn't feel that it was a good idea to set it for May 19th. Okay, the other logistical note is that I've extended homework 5 due date by 48 hours. So it's now due on Wednesday, May 12th instead of Monday, May 10th, to give you guys more time. Today, I will be beginning lecture 9. What I'm going to do is I'm going to make a supplementary video. Welcome. I'm going to make a short video that I'm going to post over the weekend to YouTube just on general second order circuits, which is one of the sections in lecture 8 that we didn't get to cover. You can forget about second order op amps. Trust me, you will thank me later if you ever look at those slides. We're not going to do second order op amps this semester. We are going to do general second order circuits, and that will be covered in like a supplementary video that I will post over the weekend. Because I really want to make sure that we have 2 lectures, two days for covering lecture 9 and 2 days for covering lecture 10. Okay. Without delaying further, it's not what I want. Okay. Sure. Okay. So today's lecture is going to be a departure from what we have been doing It's basically a review. It's largely a review of complex numbers and manipulating complex numbers. So first of all, why do we need complex numbers? This is like the perpetually confusing question to engineering undergrads. Why do we need to employ complex numbers to analyze a physical world that is purely real? And that is a good question to ask yourself. Certainly took me a long time to figure that out. And the short answer is that the laws of exponents make mean that performing a phase shift, so hopefully you know what a phase shift is, but if not, it's okay, we'll define it here. Performing a phase shift is easier when you go to complex numbers because you can phase shift a sinusoid by multiplying, whereas you cannot do that with real numbers. If you have a cosine function and you want to shift it by 45 degrees, that can be accomplished by a multiplication if you're dealing with complex exponentials. It cannot be achieved by multiplication if you're working with real sinusoids. Sure, I'll upload the video, yeah. I'll add it to my to-do list. Okay, so yeah, without hesitation. Today's lecture is on sinusoids and phasors. So a phasor is just a different way of representing a sinusoid. The theme of this lecture is the following. If we know what the frequency of a sinusoid is, then all I need to tell you to be able to reproduce that sinusoid is tell you its amplitude and its phase. And if you have that, you're set. You can recreate the signal at all times. So now we're moving into AC circuits. AC means time varying. And so we are really interested in how a circuit responds to a sinusoidal voltage. And why? Well, number one, we employ sinusoidal electrical sources in our in the electric in the power everything. There's in North America it's a 60 hertz sinusoidal excitation that comes out of your wall. So that's number one as practical relevance. Number two is that you can decompose any signal into a sum of sinusoids. And then you can use linearity so if you have a system and it has an input that is not strictly given to you as a sinusoid, you can decompose the signal into a bunch of sinusoids and use linearity to find the output as a system. And so sinusoids have very high significance in engineering systems. So again, alternating current is synonymous with sinusoidal current or voltage. And so basically the direction of a sinusoidal current reverses at regular intervals. So it goes forward, then back, and repeats that way. So there's periodicity in the natural world. If you think about the movement of the planets, if you think about the swinging of a pendulum, ocean waves, those are all things that can be well captured with a sinusoidal fluctuation. It's also very easy to generate, to transmit. So if you can easily propagate a sinusoidal electromagnetic disturbance across very long distances. That's what makes telecommunications work. And they're very easy to analyze. And the reason they're easy to analyze is for two reasons. One, the derivative of a sinusoid is a cos, and the derivative of a cos is a sine, which is very convenient. And two, is that, again, any function can be written as a sum of sinusoids because of Fourier analysis. And so It's just very practical to be able to use that as a basis for for understanding your system. Okay, so this is sinusoidal steady state. So in other words, we assume that the amplitudes of our sinusoids are fixed for all of time. That's the meaning of sinusoidal steady state, is the amplitude doesn't start out at zero and go to some value. It starts off and ends off at the same value at constant. So for example, let's consider a voltage, and now the voltage is a function of time t. And it's defined by Vm sine omega t. Okay, so I've already mentioned that omega is called the angular frequency of that sinusoid. So how is a frequency in a temporal frequency? So how long is a cycle? How often does that voltage cycle in time? Omega t together is called the argument. All right, so that omega t is really an angle. You can think of it as an angle in radians. And V of m is an amplitude, and that has a value, it has units of volts in this case. Okay, so here, I'm sure you know what a sinusoid looks like at this point. You know, a sinusoid with an argument of just t repeats every 2 pi radians. Okay? And the period of sine omega t is 2 pi over omega, where omega is defined by 2 pi f. Okay, so omega is by definition equal to 2 pi f, where f is the frequency in hertz. So this is just a little proof of the fact that sinusoids are periodic, right? So if you have your omega t, if you have sine omega t as your function, but now you replace t by t plus capital T, where capital T is constrained to be, or capital T is equal to basically an integer multiple of the distance from here to here. So remember, omega is just 2 pi f. So 2 pi over 2 pi f is 1 over f. So in other words, it's the inverse of the frequency, which is defined as the period. And the key thing to note here is that by writing capital T like this, you get this expression simplifies into sine of omega t plus 2 pi. So what does this mean? It means the sinusoid of omega t advanced by 360 degrees. But we know that sinusoids repeat every 360 degrees. And therefore, sine of omega t plus 2 pi is exactly equal to sine omega t. Right? So this is because this is just the definition of the periodicity of sinusoids. So the sinusoid of any number plus 360 degrees is going to be equal to the sine of that original number. I don't think you need to dwell too much on this little proof. The only thing you need to know that if t happens to be an integer multiple of that that 1 over the fundamental frequency, then then the function repeats with that value. Okay, so a periodic function is anything that satisfies this property. So the value of the function at time t is equal to the value of the function at t plus n capital T, where n is any integer and t is called the period. Okay, so cyclic frequency is just equal to omega divided by 2 pi. So the reason we do this is because it's just it's easier to work with radians when you're dealing with voltages and currents, and when the frequencies that we're dealing with are very large, which they often are. But remember, there's a very straightforward relationship between the frequency in hertz, it's called the cyclic frequency, and the angular frequency, which is equal to 2 pi f. Okay, so the units of omega are radians per second. So in other words, how many revolutions of that unit circle are we making per second? And f is in frequency of hertz, which translates to how often is that sinusoid getting back to its starting point. All right, so hopefully that is a review for most of you of trigonometry. Okay, so let's take a general expression such as this. All right, so our argument is everything that goes into the sine. So here the argument is omega t plus phi. And phi has a special meaning. It's called the phase angle. It's called an angle because the units of omega t are radians, right? And so if, let me just do something. Just 1 second. You're going to lose the display here, I think. Ah. Oops. You guys see my screen?
Yeah.
Okay. Thank you. Right. So where was I? Right. So the question is, what is the difference between Vm sine omega t and Vm sine omega t plus tau? So first of all, who can answer that question? What is the difference here between V1 and V2? Just in terms of the way they look. Do they go up and down? Do they reach the same heights?
They have the same height and the same like period or frequency.
Yeah, that's right. They do. But how are they different?
One is at the initial point, and the other is one for rotation.
Yeah, exactly. We said that they're phase shifted. So the dashed line here is V2. So this here is V2 because at time 0, it is not at 0, right? So the sinusoid at 0, so when the argument of the sine is 0, the value of the function is 0. So the solid line is V1 and the dashed line is V of m. And the way to think about this, because this can be tricky to understand which one's ahead of the other, and you really need to be clear as to which sinusoid is ahead of the other. That's very important for lectures 9 and 10. And so the dashed line, hopefully you all agree, is ahead of the solid line. And the reason is that it hits its, let's call this the starting point and this the starting point, right? These 2 points are the starting point. V2 gets to its starting point earlier than V1. Another way of looking at which one hits its peak first. So V2 hits its peak before V1, right? So this is the past, this is the future, this is the present, right? So V2 hits its peak first, and therefore we say that V2 leads V1. Another way of saying this is that V1 lags V2, and phi is sometimes called a phase lag. And so when phi is positive, then V2 is ahead. If phi is negative, then V2 is delayed. All right. Here are some very useful trigonometric identities. So if I take the sine of two angles, the sum or difference of two angles, then that can be expressed as the product of the two angles. But so I don't know how else to say this in words. Sine of A plus B, for example, is equal to sine A cos B plus cos A sine B, where sine of A minus B is equal to sine A cos B minus cos A sine B. And the reason that this is important is that if we take B to be either 90 degrees or 180 degrees, then you get these very special cases that are useful. And so, for example, if you said B is equal to 180, if you said B is equal to 180, then you get that the sine omega t plus 180 is equal to minus sine omega t. The cosine of omega t plus 180 is equal to negative cosine omega t. So what does this mean? It literally means that if I shift forward by 180 degrees or shift backward by 180 degrees, I will see the same signal, just inverted along the y-axis. Okay, so these you kind of have to memorize, unfortunately. But they're not particularly difficult to understand, especially the first two. The first two just means that whether you go left or right by 180 degrees, you always end up with the same signal, just with a negative sign. Then the last two identities here say that if I advance a sine function forward by 90 degrees, then I get to a cosine. And if I delay a sine function by 90 degrees, I get a negative cosine. Right, and so, see if I can draw this in a way that convinces you. Right, so this is 0, pi to 2 pi. Right, so if you have, let's just take so if I take sine of omega t plus 90, so that's me, instead of this being 0 here, instead of this point being the starting point, then this becomes the starting point. Right? The starting point becomes 90 degrees. And so you can see that if this is my new signal, that is in fact a cosine. Right? So if I take my sine, but I started with a head start of 90 degrees, I end up with a cosine. On the other hand, if I take my cosine and I do the same thing, so if I take the red as my cosine, if I start it 90 degrees forward, I end up with this function, which is a minus sign. And so these are very useful identities because they allow us to switch back and forth between a sine and a cos. And if you have a negative amplitudes, we don't like. We always want you to leave your sinusoids in terms of ideally cosines, but definitely with a positive amplitude, because negative amplitude is just confusing, right? We want the amplitude to be positive. And so these first two identities allow us to switch back and forth between a positive sinusoid and a negative sinusoid. And the last two allow us to switch back and forth between sines and cosines. All right. So do I want to say anything about this? Not really. I'm not a big fan of this slide. This is just showing you that because sine and cosine are orthogonal, so if you think of if this is the cosine dimension, and this is the sine dimension. And so if you go A in the cosine direction and B in the sine direction, then the net result is out here. This is the net vector. And it has a value, it has an amplitude. It has an amplitude C and a phase angle theta. And it's not hard to see that the value of C is just, you just use the Pythagorean theorem, because the sine and the cosine have a 90-degree relationship between them. And also you can get the theta, the phase angle of this vector, of the summation of a sine and a cosine, by taking the arctangent of B over A, right? Where this is B and this is A. It's not really that important. I don't think it's anything super interesting here, but the point is you can add a cosine to a sine if they're at the same frequency by using this identity here. All right. And this is just a demonstration of what I just said. Basically, if you add 180 degrees to a sine, you get a negative sine. If you delay a cosine by 90 degrees, you get a sine function. Okay, I'm going to skip all the examples, and I'm going to do all the practice problems, because the practice problems in this lecture, the practice problems are like a mirror of the examples. And so I want to do the examples with you guys. So we're starting off pretty straightforward. Given the sinusoid 5 sine 4 pi t minus 60, calculate its amplitude, its phase, its angular frequency, its period, and its cyclical frequency. So who can tell me the value of the amplitude, first of all? Five is right. What about its phase angle? Minus 60 is correct. What about the angular frequency? Remember the definition. Remember, omega is equal to 2 times pi, 4 pi. That's a good, yeah, it's 4 pi. Thank you. Well done. Now, what else do we need? We need the period. So let's actually get the frequency first. I think it's easier to get the frequency first and then the period. What's the value of the frequency in hertz?
2.
2, excellent. How did you get that?
It's the angular frequency over 2 pi.
Exactly. And then the period, if the frequency is 2 hertz, then the period is equal to what? 1/2 second. Thank you. So this is a sinusoid with a period of 500 milliseconds. All right. Okay, let's see, do I want to do this? I think there's an example, a practice problem that I would rather do. Okay, I like this one a lot. I like these questions. And maybe for these, what I'll do is I'll write the identities on the slide. Oh, Give me a second. Ah. I think what I'll do is I will write the identities on the slide just to make it easier for you guys. So W actually means omega. And then we have sine t plus minus 90. That's right. Okay. So those are the identities. And the question we'll ask, we're given two sinusoids. The first sinusoid, first of all, has a negative amplitude, which we don't like, and it's also a sine. The second one has a positive amplitude and a cosine. So in general in this class, the convention that we use is that we work with cosines. And those cosines have to have positive amplitudes. And so when you do questions like this, the goal is always to get both phasors, or sorry, we're not phasor, both sinusoids into the form of a cosine with a positive amplitude. So how do I transform I1 in terms of a cosine? Which identity can I use? Add or subtract 90. Yeah. That right. Right. So we want to basically is it my cursor here again? We basically want to use the bottom one. Right? We want to get to positive cos. We have negative sine. And so we want to use we want to use this identity. Cosine of omega t plus 90 is equal to negative sine omega t. So in this case, negative sine omega t, and I don't know how, is the analogy here is minus 4 sine 377 t plus 25. Okay, so okay. All right, let me see if I still have my, okay. So who can tell me how I can write I as a positive cosine? So what I'll tell you is that the amplitude is going to be 4, and the angular frequency is not going to change. Frequency is not going to change. But what do I do with this phase angle? Do I add 90 or do I subtract 90?
Subtract.
We add, actually, and give me a second. This is going to drive me crazy. Let me just quickly see what the chat answer was. Add, yeah, so it is add. And the reason that we add is because, let me just see. is that we want to use, we want to use this identity, which means that we have to add 90 degrees to turn a negative sign into a positive cos. And so I1, actually, I think I have this animated, so I'll just go with, right. So we turn this into a 4 cos 377t plus 25 plus 90 degrees. And now we have I1 as a positive cosine and I2 is a positive cosine, right? And therefore, which one is ahead of the other? Is I1 ahead of I2 or is I2 ahead of I1?
I2 leads.
Yeah. No, I1 leads. Sorry. And the reason is, it's very easy to get these confused, by the way. These can make your head hurt sometimes. And the reason is that the phase angle of I1 is plus 115, and the phase angle of I2 is minus 40. So I1 is 155 degrees ahead of I2. So the phase angle between them is 115, and I1 leads I2. So the picture that you would draw for this is the following. So if you have your imaginary and your real, this is your real, your cosine, this is your imaginary or your sine. Then I1 has a phase angle of 115. Okay, so this is, so the length of this line is 4. And then I2 is has an angle of minus 40. So somewhere here. And the length of this line is 5. Okay. Length of this line is 4. And so the angle between them is 155. So another kind of way to see which one's ahead is that they're going this way. This is the angle of rotation, right? So we're going counterclockwise around the circle. This is the starting point. This is, and then back to the end, right? So we're doing this. So the red is always going to stay 155 degrees ahead of the green here. All right. So now we get into phasor. So a phasor, honestly, it's just a technique that we use to express sinusoids. So again, the basic idea is this. If I tell you the amplitude and the phase of your sinusoid, and we're all in agreement as to what frequency we're working with, then you can represent your sinusoid across all time if you just know the amplitude and the phase. Okay, so strictly speaking, a phasor is a complex number, and that complex number has a magnitude and an angle. So the magnitude represents the amplitude and the angle represents the phase. So because phasors are complex numbers, you guys need to be familiarized with complex arithmetic. So first of all, what is a complex number? Well, it's defined as x plus jy, where j is called the imaginary unit, canonically the square root of -1. I think you all know this. Just think of the x and the y as occupying a two-dimensional space where the two dimensions are orthogonal to each other. In other words, I can play around with this value of x. It never changes the value of y. So I can play around with the value of y, it never changes the value of x. So in other words, it's like east, west, north, south. If I move 5 paces east, I haven't changed latitude, right? So it's the same idea, orthogonal axes. So there are three ways of representing a complex number. I need to be familiar with all three. But it's very straightforward to switch back and forth. What I'll say is the following. First of all, if you want to know, the polar form has a radius and an angle. The exponential form has a magnitude r and a phase angle. So here's how you know which one is best to work with. If you're performing addition or subtraction, then it's best to be in the rectangular or Cartesian form. If you're performing multiplication or division, then you should be in either polar or exponential form. Okay, so multiplication and division is easy if you're in one of these. Addition and subtraction is easy if you're one of these. And I think you're all familiar with, for example, to get the radius from the real and imaginary parts, you just take, you just use the Pythagorean theorem and you use the arctangent to get the angle. And so here's an example of a complex number z that's drawn on the real and imaginary plane. Right? So the x coordinate is called the real component. The y component is called the imaginary. And the length of this line is, is the value r, and phi here is the angle between this phasor and the x-axis. So now, what happens if you want to add Z1 and Z2 together? Well, it's easy. You add their real parts, and separately you add their imaginary parts. Okay, so for example, addition, if you want to add Z1 to Z2, you add X1 and X2, and that becomes your real part. And then you add Y1 and Y2, and that becomes your imaginary part. Subtraction is analogous. Right. So this is true. I mean, if you just add this to this, you easily obtain this. On the other hand, multiplication and division, it's best to do in polar form or exponential. And the reason is because of laws of exponents. So if you multiply, this is the base, and this is your exponent, right? So I probably didn't say that right. It's actually easiest to think about it in exponential. Yes. So r is not really the base. E is the base. E is the common base, and r is like the constant in front of the base. So the point is that if you multiply Z1 and Z2, that is equivalent to multiplying their magnitudes and adding their phase angles. And so you can also multiply two numbers in Cartesian. It's just more work. You have to go x1 times y1 plus x. You have to do the multiply two binomials. Division follows the same rules multiplication, except now you're dividing the magnitudes and you're subtracting the phase angles. Again, that's all because of the laws of exponents. Now the reciprocal, right? So the reciprocal, so if you have, maybe I'll try to write this out. So if you have 1 over r times power e to j phi, that's equal to 1 over r times e to the minus j phi, which is equal to 1 over r, the exponent of negative phi. Okay, so another way of viewing that geometrically is if you have, Well, actually, I don't know how to view geometry. I was gonna say I know how, but it's actually, so if you have a vector that has a length of 2, and you want to reciprocate it, it points this way, and it has now a value of 1/2. I'm not sure if that has an easy geometric interpretation. The phase angle has a very nice geometric interpretation, but the shortening from 2 to 1/2 does not. Square root, I think it's pretty straightforward. The conjugate is an important one. The conjugate is one that we use a lot. And so the conjugate of a complex number is where you leave the real part intact and you negate the imaginary component. And so negating the imaginary component is equivalent to negating the phase angle, right? Because you're moving, if you have, oops, let me see if I can, if you have a complex number like this, and all of a sudden you make the negative, you make the negative component, sorry, you make the imaginary component negative, you're effectively moving it down here. And so your phase angle was this angle, this was phi, and now it's this, which is minus phi, right? Because this is treated as a positive angle, and this is treated as a negative angle. Hopefully I haven't confused too many of you. All right. If there's any questions, by all, please jump in and ask me. There's nothing wrong with being rusty on your complex numbers. And if you need a reminder, by all means, let me know. This is a super cool property. 1 over j is equal to minus j. So you can move j's, you know, from the numerator to the denominator and vice versa, simply by switching, by adding a minus sign. This is still one of the most fascinating. The fact that this theorem has a proof is mind-blowing for me. So e to the power of j phi is equal to cos phi plus or minus j sine phi. This is super useful because this allows us to work, to transform or to move back and forth between complex exponentials and real sinusoids. And so here is where, this is the answer to the question, why do engineers work with complex numbers? Well, the reason is this. I know that my sinusoid, I know that there is no such thing as imaginary numbers in the real world. However, I can represent my real physical quantity as if it was a complex number. And the operations on that complex number are easier to do, right? And the reason they're easier to do is because, for example, if I have a complex number, ej phi, and I want to phase shift it by 90 degrees, all I have to do is multiply it by ej phi over 2. So this is a multiplication. On the other hand, if I have cos phi, if I want to phase shift cos phi, if I want to make it equal to cos phi, pardon the poor handwriting here, phi plus pi over 2, the operation from here to here is nonlinear. This cannot be achieved by an addition or multiplication. This can, right? And that's why, because now I've transformed a sinusoid with a phase angle of phi to a sinusoid with a phase angle of phi plus pi over 2. Right? And I've done it simply with a multiplication, whereas it's not possible to do that with real numbers. So hopefully I've spared at least one of you the agony of not understanding, like I didn't for many years, why it is that engineers work with complex numbers. I think this is the only reason. I'm trying, like, in general, there are some other properties of complex numbers that are handy, but I think this is the biggest one, is that a phase shift can be accomplished by a multiplication. But once we're done with analyzing our complex sinusoids, we can, at the end of the day, we're going to transmit a real number on that antenna or that electrode or whatever. And so we transform it back to a real number simply by taking the real part of our complex exponential. All right. So in other words, VT, VT is the real part, and this notation is a little bit kludgy, and if it's not immediately accessible what this is trying to say, don't worry. All it's really saying is that a real cosine is just the real component of a complex exponential. And the complex exponential has a magnitude of V of m and a phase angle of phi. And this is the big thing that's in the red box here, is that the boldface V is called the phasor. And the phasor is the quantity that stores the magnitude and the phase of our sinusoid. So if I know the phasor V, then I can reconstruct the sinusoidal time domain signal V of t. So for example, if I tell you that V of m is equal to 5 and phi is equal to 45, then I know that V of t is equal to 5 times cos omega t plus 45. Oh, real part just means, yeah, real part. RE means real part. So let me just get my cursor back. So where is it? So if I have that's all it means. You're pulling out only the real part. All right, let me just fix my all right, did this. So basically what this means is that it's like a transformation of a sinusoid from one domain, which is the time domain, into the phasor domain, which is really the frequency domain. And so it's like if I want to describe a sinusoidal signal to you, there are two ways that I can go about it. I can say for every single time instant, I can tell you its value. That would be a very redundant way of communicating to that sinusoid, because there's a redundancy there. We know that the sinusoid repeats. So instead, I may just say, you know what? I have a sinusoid that has a magnitude of Vm or amplitude of Vm and a phase angle of phi and some frequency omega. And that is called the phasor. Okay, so it's just another domain. Engineering is all about transforming our data from one representation to another. Okay, so another way of thinking about it is if your phasor is spinning around the unit circle and its projection on the real number line is equal to is going to give you the cosine function. And so if this phasor is spinning around and at every time instant you measure its projection onto this line, you get this shape. So this is now a function. So time here is going around and around the circle. Time here is on the x-axis.
Professor, you're not sharing your screen anymore.
Oh, that's very unfortunate. I was doing all kinds of gestures. All right, sorry. Yeah, so what I was saying is, this is your phasor, and it's going around and around, right? And at every time instant, its projection onto the real number line is the value of this sinusoid here. So time here is on the horizontal axis, time here is around the circle. And so if you just think about this bold-faced phasor spinning around, its projection onto the vertical axis is the value of our v of t, which is the real component of this phasor. Okay. See if I wanted to say anything else. And basically, the angular frequency here is how many radians you go through per second. So if every second you start and end on this line, your angular frequency would be 2 pi radians per second. That would be, if you made it around the circle once per second, your frequency would be 2 pi. If you made it around in half a second, your frequency would be 4 pi, right? Yeah, this is a difficult thing. I hope that some of you are able to get this. If you don't get this, it's really okay, because you can use the tools of phasors without really understanding deeply what they are. But it's always nice to have kind of a geometric grasp of concepts. Although I will say that I certainly do not have a geometric grasp of every concept in engineering. But the more it's satisfying when you do. Right. So if I set t is equal to 0, then this term goes to 1, and you're left with just the phasor v. So now we are going to be omitting the e to the j omega t term. So when this whole thing is a phasor, but we will typically omit the complex exponential, and we're just going to write the bold phase v. And so keep in mind that the e to the j omega t is still there. It's just that we're going to omit it just to make our notation a little bit more brief. And keep in mind that when working with phasors, we have to agree on what the frequency is. So the idea of a phasor works for one frequency at a time. If you introduce another frequency into the circuit, you have to do a whole different set of phasors. And we'll do some examples of that in chapter 10 when we do more than one frequency. Do you guys see my screen now?
Yeah.
Okay, you do. Okay, good. And so a phasor is a complex number, right? Which means that we can represent it either in rectangular form or in polar form or exponential form. Oops, went by fast. Okay, so a phasor has a magnitude and a phase angle. So here are two examples of phasors, the greener phasors. So this is a voltage phasor. So this capital bold phase V is representing a voltage that's sinusoidal and has an amplitude of that is equivalent to the length of this phasor, and its phase angle is this angle here, phi. And negative phi is, so this is another phasor. This is for representing a current, and it has a magnitude of Im and a phase angle of negative theta. So the important thing is that time is flowing counterclockwise here. Right, we start off here, and we go around the unit circle. So to kind of harp on the point, these two, what this symbol means that these are interchangeable. In other words, I can represent a time domain function Vm times cos omega t plus phi as a phasor. It's a complex number. So this is a real number, a bunch of real numbers, and this is one complex number, right? This is actually, it's actually an important distinction. This is a whole series of real numbers. This is a single complex number, right? So it's going back to that point. If I wanted to describe a sinusoidal function to you, I could just tell you its value at every time instant, or I could give you its phasor. This is more compact of a representation. And so how do we go back and forth between time domain and phasor domain? Well, the easiest way is if you have a cosine with a positive amplitude, then the amplitude becomes the magnitude, and the phase angle becomes the phase angle of your phasor. If you have a sine function, you just need to add a minus 90-degree phase shift. Why? Because we work with cosine. We are by convention, we work cosines. So remember the identity that let's see, what's the identity that I want here? Minus 90. That's the identity that I want. Right? Because of this identity, if my signal is a sinusoid, not a cosine, I have to add a minus 90-degree phase shift to my phasor. The good news is that in many of the questions that we will be covering, the circuit quantities are actually going to be given to you as phasors, right? And in that case, you don't even have to do the transformation. All right. So if you want to represent your sinusoid as a phasor, you just write it as a cosine, and the magnitude becomes your amplitude, and the phase becomes your phase angle. So again, this is a common practice in engineering, is to take a signal and represent that same signal in another domain. So this is really a precursor to the Fourier transform or the Fourier series, which you may have covered before. Okay, so it's often commonplace to refer to the phasor domain as the frequency domain. And the reason is that we are working with one frequency at a time. Right? So again, if your frequency omega changes, then you have to redo all your phasors. All right, so here is a derivation that probably will puzzle many of you, and it has to do with what happens when we take the derivative of a cosine. Right, so we know that the derivative of a cosine, maybe I'll try to write this out to at least try to unpack it. So v prime of t is equal to Vm times omega times -1 times sine omega times t plus 5. Give me just 1 second. So what I was trying to say is that if you have if VT is equal to VM, then the derivative of that, V prime T, is equal to negative VM times omega times sine omega times T plus phi. Okay. And so why do we bother with this? Well, if you trace this derivation, what you see is that, okay, Josh, really would like to have and keep my cursor here. I think I have to exit out of the slideshow. Okay. I'm going to try to teach this. All right. Okay, so this is just a derivative. This first step is just a derivative of a cosine, is a negative sign, with the chain rule applied. In the next step, we know that our phasor has to be expressed as a cosine. So what we do is we transform our from a sine to a cos, and we do that by adding a 90-degree phase shift and removing the minus sign. And there's an identity that transforms a negative sign into a positive cos with an extra 90-degree phase shift. And here's the part that is a little bit terse. So what have we done here? So we know that a cosine is equivalent to the real part of a complex exponential. So instead of leaving this as a real number, we represent it as the real part of a complex number. And that complex number has three sinusoids. It has the original omega t, the phase angle of the original phase angle of phi, plus this new term, the phase angle of 90. And if you think about what does e to the j90 mean, right? What does that mean? So it literally means this. So your phasor, right? So in other words, e to the j90 is equal to j. And you can also see that if you just apply Euler's theorem to this. The cos of 90 is 0 and the sine of 90 is 1. And so this transforms to this. And what this result is saying, that if you differentiate a function in time, in the phasor domain, that's equivalent to multiplying it by j omega. So you may have seen this result elsewhere in math, and it's another one of these results that I had a very hard time grasping when I was in school. And so basically what it means is that the derivative of a high frequency signal is large, and the derivative of a low frequency signal is small, right? So if you think about, you have one sinusoid that has a high frequency, and you have another sinusoid that has a low frequency, right? The derivative of this is going to be high. Why? Because this thing is changing fast, it's going up and down fast. The derivative of this is going to be slow because it's changing slowly across time. And so what this is saying is that the derivative of a sinusoid is proportional to the frequency. So that explains the omega. The J just means that when you take the derivative, you're shifting your signal by 90 degrees. So if you differentiate a sine, you get a cos, right? And the phase angle between the sine and the cosine is 90 degrees. So this relationship just means that when you differentiate a signal in the time domain, that's equivalent to phase shifting and linearly and multiplying by the frequency. So in other words, a high frequency sinusoid will have a large derivative. A low frequency sinusoid will have a small derivative. All right. Let me make an attempt at slideshow once again. Okay, so differentiation in the time domain is equivalent to multiplication in the phasor domain. And so this is a kind of another example of why working with complex numbers is useful, because multiplication is an easier operation to perform than differentiation. And there's a similar property where the integration in the time domain is equivalent to division by j omega in the phasor domain. In other words, integrating something that is moving fast is gonna bring down your phasor. Integrating something that's moving slowly is gonna bring up your phasor. So that's the omega. And similarly, there's a 90-degree relationship between a sinusoid and its integral. And so, excuse me, what these slides are trying to convey is that differentiation and integration can be handled more conveniently in the phasor domain. Let's see. Okay, so again, what are the differences between V of t and boldphase V? Number one, V of t is a time domain function. So it's a function of time. Boldphase V is not a function of time. It's a function of frequency. Lowercase v is a real number. Boldphase V is a complex number. Lowercase v is a dependency on time. Boldphase V does not. V of t is always real, while capital boldphase B is generally a complex number. And again, the last point bears repeating, namely that this only applies to the case where we hold frequency constant, right? As soon as and you can see this here, if omega changes, then my phasor changes. All right, I'm going to skip the example, and I'm going to hopefully solicit some of your guys' help to help me do some complex arithmetic. So I am tasked with multiplying these two complex numbers and then subtracting this one and finally conjugating. So if I want to evaluate this complex arithmetic, what would be my first step?
Transform it all into polar or exponential.
Yeah, that's right. That's excellent. You definitely want to transform everything into polar, right? Because the first thing that we need to multiply these two together. And to multiply these two together, the easiest thing to do is to work in polar. And so you're going to multiply 5.38 times 4.12, it's going to be about 20. And then you're going to subtract 104 from 21.8. So now we have this, this is where we are now. So we have a polar number minus another polar number, all conjugated. So what is my next step going to be here? Is it easy to subtract polar numbers?
Move it back to Cartesian.
Yeah, exactly. So to go from polar to Cartesian, you change to a magnitude, the magnitude is 22.17 and the angle is 125.8 degrees. So this here is the Cartesian representation of this. And this here is a Cartesian representation of this. So 5 angle 60 is equivalent to 5 cos 60 plus 5j sine of 60. And now I can simply group the real terms together and the imaginary terms together. And so I get minus 15.5 plus 13.65j. And I have to conjugate that. So I simply negate the coefficient on the imaginary term. And if I want to put that, and I could have also put that into a polar number, but I chose not to here. It's always acceptable to leave the answer in this form. Okay. What about this one? What would be the first step in approaching this problem? Which number do I want to transform first?
You want to transform all the Cartesian into polars for the division. Wait. You want to transfer the 3 to 40 to Cartesian first.
Yeah, exactly. That's right. First thing I want to do is I got to transform this guy into Cartesian so that I can simplify the numerator. And I'm just going to go ahead and transform tan angle 30 as well, because I know I'm going to need to add it. So anytime you see addition, you know you're going to need to work in Cartesian. But now I'm going to evaluate. So I'm going to now simplify the numerator. And I have to divide one complex number by another. So here, there's an intermediate step of converting this into both the numerator and the denominator into polar numbers. Because in polar form, it's easiest to multiply and divide. So I'm going to divide 14.1 divided by 5, and I'm going to subtract 127 from 29.3, because those are the exponents. Okay. So now I have a polar number plus a Cartesian number. So the easiest way now is to represent the polar number as Cartesian. And now I just have the sum of two Cartesians, which is 8.28 plus j times 2.2. Okay. Is there any questions on how to manipulate complex numbers in rectangular, polar, and exponential form?
Professor, I have a question.
Sure.
How do we go from the second last step to the last step?
Yeah, sure. So we so we're gonna have this. This is gonna, you're gonna use your calculator to evaluate this real number. and you're gonna use your calculator to evaluate this real number. Right? And those get added together, and that becomes 8.28. And then you're gonna evaluate this number and this number, and those get added similarly. And that works out to be 2.2. And this works out to be 8.28. And so the J is like, it's like a, you know, everything with a J has to be grouped together. So the, I don't know, let me try one more way of, so you can have, for example, it's going to be 2.8 cos negative 97.7 plus 10 cos 30 plus, and then we're going to put the J out front, 2.82 sine negative 97.7 plus 10 sine 30. And so we're grouping the real parts together and the imaginary parts together. And the sum of the imaginary parts has to have a J in front of it.
Got it. Thank you so much.
Okay, you're welcome. I really encourage all of you to ask questions if you have them on this, because this is, I guarantee that there's nothing super complicated about complex numbers and about complex arithmetic. So if you have a gap in your, comprehension of complex analysis, you know, by all means, let me know. I'll try to help. All right. Skip this. Okay, we're going to do this. So I need to transform minus 7 cos of 2t plus 40 into a phasor. So one problem is that, so I have it as a cosine, however, it's got a negative amplitude, which I don't like. Right? So I need to know, I need to change this into a cosine with a positive amplitude before I can pick off the VM and the phi here. So how can I switch negative 7 cos of 2t plus 40 into a cosine with a positive amplitude?
Or subtract 180 degrees.
Yeah, you can subtract, you can also add. It's either way works actually. Right, so I'm going to add here, but this could have been minus 180 as well. Right, so to go from a negative cos to a positive cos, you can add or subtract 180 degrees. And so the answer becomes 7 cos 2t plus 220. In other words, my phasor is V is equal to 7 angle 220. And if you did minus 180 here, it would have been 7 angle minus 140. Right? And the reason that those are equivalent, I can get, if this is the unit circle, then plus 220 degrees is like here, right? And minus 140 would be here, right? So it's the same angle. So there, I could have easily written this as 7 angle negative 140. What about this question? Oops. Yeah. What about I is equal to 4 sine 10t plus 10? I need to get that into a cosine with a positive magnitude. So what do I have to do to change it from a sine to a cosine here? So I'm either gonna need to add 90 or subtract 90. You guys remember which one it is?
We add 90.
It's good, guys. It's actually subtract here. And the reason is, I appreciate you guys being active. So if I have a sign, if this is my 0 point, if I, what did I want to do? Oh, I wanted to do the other way, I guess. If I want to do it, I wanted to draw a cosine. So if this is my cosine, if I go 90 degrees in negative direction, then I have a sine function, right? That's my positive. So this is that, and this is the black. And again, you can just confirm that by calling the appropriate trigonometric identity. So that becomes 4 of cos 10t minus 80. So the magnitude is 4, and the phase angle is minus 80. And that's all there is to it. This is the nice thing about phasors. It's really, as long as you know how to go back and forth between cosines and sines and negative coses to coses, negative sines to sines, then this stuff is really easy. You just need to know what the amplitude and the phase angle are, and you have the phasor. I'm going to erase this, skip this. Okay. So if I want to convert, if I have a phasor and I want to convert it to a sinusoid, for example, this one, how do I do that? How do I go from a complex phasor to a real sinusoid here? I guess I can just do the first one with you, right? So the first thing you do is just pick off, and this is really not a good way of writing a phasor, but that's what we were given. So the amplitude becomes -10, and the phase angle becomes 30, right? And to switch, and you can either add or subtract 180 to changes from a negative cos to a positive cos. Now this one, we have to do a little bit of work first, because it's presented to us in Cartesian form. And so the first thing we need to do is to simplify this, to convert this rather into polar form. So this is going to be 5j minus j squared times 12. Oh, sorry, I wasn't done this one. Right, so this is 5j plus 12, right? Because j times negative j is equal to plus 1. And so using the Pythagorean theorem, the magnitude of this phasor is 13. And the phase angle is 5/12. And to see that, again, I'm just going to draw it out. All right, so this is 12 units here, and 5 units here. So this is my phasor. And this angle here, this is 5, and 13 is the distance from here to here. That's my 13. Okay. And so my sinusoid just becomes 13 cos omega t plus 22.62. Is there any questions on how to go back and forth between time domain and phasor domain? Okay. Let's see. I don't like this example at all. Let's do this one. So let me clear the annotations. Okay. So, well, you have the answer here, which is unfortunate. But I want to add, so I have a sinusoid and I have a cosine, and I want to add them. And so there's a couple of different ways that you can go about doing this. But one way is to represent them both as a phasor. So -10 sine omega t plus 30 is equal to, so the first step is to transform from a negative sign to a negative cos. So here's we're going to have two steps, right? So to go from a sine to a cos, you have to add a phase shift of 90 degrees. Or sorry, you have to subtract the phase shift of 90 degrees. And now you go from a negative cos to a positive cos. And so negative 10 sine omega t plus 30 is equivalent to 10 cos omega t plus 120. So that the important thing is that that can be written as a phasor. And I'll try to draw this. So 120 degrees is over here, and the magnitude of that phasor is 10. Okay. And then now let's do the same thing for V2. So the phasor corresponding to V2 is easier to identify because we have, we're given basic, it's already represented as a positive cosine. So the magnitude is 20 and the phase angle is -45. So notice that this is a phasor, is a complex number, and this is a phasor, is a complex number. So we are asked to add them. And so adding sinusoids seems difficult, seems involved, whereas adding complex numbers is not as bad. We literally just have to transform these into Cartesian notation and then add them up. So V1 in Cartesian form is equal to 10 cos 120 plus j times 10 of sine 120. And V2 as a rectangular complex number is equal to 20 cos -45 plus j times sine of -45. So all we've done here is gone from the time domain to the phasor domain. And from the phasor domain, we've just gone into Cartesian form. And now that we have the numbers in Cartesian form, we can add the real numbers together. So these two get added up, and that becomes this. Right? So 9.14 is equivalent to 10 cos 120 plus 20 cos -45. On the other hand, if you take 10 sine 120 and 20 sine -45, you add those up and you get -5.48. And now you have a Cartesian complex number. And so how do I get this 10.66? Well, it's just the square root of 9.14 squared plus 5.48 squared. That's our magnitude. Let's call that m. And my phi angle here is just the arctangent of negative 5. That's a 5, I promise. Negative 5.48 over 9.14. And that becomes negative 30.94 degrees. Okay. And then finally, when we have the number in polar form, it's easy to go back to the time domain sinusoid. So if you're wondering what this question is all about, it's just trying to convince you that if you want to add a sinusoid to a cosine, a somewhat easier way is to convert them into phasors, add the phasors, and then go back to the sinusoidal domain. Let me see where we are. All right. This is good progress. I don't want to keep teaching for today. We only have 2 minutes anyways. And I think we're very close. Yeah, we're very, very close to the application of phasors into circuits, which is really what we did today is just to prepare you for how to use phasors to analyze AC circuits, which we will cover on Monday's class. Okay. Thank you to those of you who stuck around. Reminder that homework 5 is due next Wednesday. I've posted the final exam date to be Monday, May 24th from 10:30 a.m. till 12:45 p.m. If you have a conflict, please let me know as soon as possible. I wish you all a good end of week, a pleasant weekend, and look forward to seeing everybody back here on Monday. Bye for now.